Anyone who's completed high school chemistry knows about atoms. An extremely tiny nucleus orbited by even smaller electrons. But what keeps the nucleus together? Heck, what keeps the protons and neutrons inside the nucleus together? 2 words: strong force. The strong force is one of the 4 fundamental forces of the universe and is pretty complicated, so we'll start with the basics. From there we can work our way up. So if we're talking about strong force at its most primary level, we have to begin with quarks and color. Quarks and their counterparts, antiquarks, are some of the fundamental elements of matter. They are what make up stuff like protons and neutrons. Color, on the other hand, is the property that strong force stems from. Color, in this sense, doesn't actually have anything to do with how we think of the word. This color is more analogous to electrical charge than anything else, so I'm going to refer to it as color charge for the remainder of the video. Just like the electrical charge dictates how a given object interacts with the electromagnetic force, color charge determines how an object interacts with the strong force. Further, those objects that don't possess a color charge don't interact with the strong force, mirroring how objects without an electrical charge aren't affected by the electromagnetic force. Unlike electromagnetism's positive and negative charges, however, color charge has 6 of these sort of states: red, blue, and green for regular quarks, as well as anti-red, anti-blue, and anti-green for antiquarks. This is important because it affects how quarks are allowed to manifest in nature. Due to some of the intricacies in strong force, quarks are only allowed to exist when their colors are cancelled out. For example, protons and neutrons are baryons, a type of particle that is made up of 3 quarks. Each of these quarks must have a different color charge: 1 red, 1 blue, and 1 green. These colors are constantly changing, but there's always one of each. The strong force acts almost like a rubber band on these quarks. As they get further apart, it begins to pull them back into the baryon with an immense force. That force is so powerful, in fact, that it has a residual effect outside the protons and neutrons. It keeps the nucleus together. In the helium atom, there are 2 protons and 2 neutrons. Electromagnetism, though, states that like charges repel each other. At this size, gravity's effect is negligible. The repulsive power of the electromagnetic force, however, reaches as high as 136 newtons between 2 protons. That means the residual strong force counteracts over 30 pounds, nearly 14 kilograms, of force in a space even smaller than an atom, just to keep the entirety of matter together. I guess there's a reason it's called the strong force.